Hi. In today's video, we are going to continue the discussion that we started yesterday. So we had done 5 problems yesterday, and we are going to start with problem number 6. I hope you can hear me. Right. So I had given a couple of problems as homework. This was the first one. Find all pairs m and n of positive integers satisfying the system of equations, satisfying the equations GCD of m and n is equal to m minus 12, and LCM of m and n is equal to 4n minus 12. We have to find all the pairs of m and n positive integers which satisfy these two equations. So the obvious first step here is to remember the standard result that the product of the two numbers is equal to GCD of m and n multiplied by LCM of m and n. Yes. So this result we have to use here. So if you try to use this result, what we can say basically now from this is that mn is equal to m minus 12 times 4n minus 12, right? So let's simplify this a little bit. If you simplify this, you get mn is equal to 4mn minus 48n minus 12m plus 144. So taking all the terms on one side, you will get 3mn minus 48n minus 12m plus 144 is equal to 0. So we can divide by 3 here, and you get mn minus 16n minus 4m plus divide by 3, this will be 48 is equal to 0. Right. So think about it. How do we try to simplify this? Again, we use the same factorization method that we have seen earlier. So notice here, if you take n common, you'll get m minus 16, but I don't have a suitable term here. So I have a minus 4m. So I need a m minus 16 factor. So I can do a plus 64. So then I have to add a minus 64, and there is a plus 48 anyway. So what have I done? I have added and subtracted a 64 here in order to factorize it with m minus 16 as a factor. So you will get n times m minus 16 minus 4 m minus 16, and this is covered now. Now you have a minus 16, so is equal to 16. This minus 16 can be taken on the other side, right? So finally, you will get this equation, n minus 4 times m minus 16 is equal to 16. This is the equation that we have to solve, and this is pretty easy. However, you have to be a little careful. So let's write it on the next screen. So we have an equation like this, m minus 16 times n minus 4 is equal to 16. And we have to solve this and find all the pairs of positive integers which satisfy this. Also remember that GCD of m and n was what? M minus 12. And LCM of m and n was 4n minus 12. And if m and n are positive integers, you should know that GCD and LCM are both greater than 0. GCD and LCM must be greater than 0 for positive integers. So basically from there, you can realize that m minus 12 must be greater than 0. And this also must be greater than 0. So that gives us m is greater than 12 and also gives us n is greater than 3. So whatever answers you get from here, they have to satisfy this condition. M must be bigger than 12 and n must be bigger than 3, right? So now it's about solving this equation. So think about this now, how to get product equals 60, right? Uh, okay, so because m is greater than 12, we know that m minus 16 is greater than 12 minus 16 is equal to minus 4. So we have m minus 16 is greater than minus 4. So basically, since we have to use integers only, we can say m minus 16 is greater than or equal to minus 3. I hope you understand what I am saying right now. Because of this condition, I can say that m minus 16 is greater than minus 4, which is the next integer greater than minus 4. It is minus 3. Right? So this inequality is correct. Similarly, n minus 4 is greater than 3 minus 4. So n minus 4 is greater than minus 1. So we can say n minus 4 should be greater than equal to 0, right? These two conditions have to be true, right? And now you think of all the factors of 16, right? So you can start by saying 16 can be written as 16 into 1, in which case m minus 16 is 16 and n minus 4 is 1. And from here, you get m is equal to 32 and n is equal to 5, right? That is one possibility. Then you can write it as 8 into 2. And then you can get m minus 16 is equal to 8. M is 24 and n minus 4 is equal to 2. So n is equal to 6. So that is another possibility, right? Similarly, you will get multiple more cases. You will get the case where it is 4 into 4. You will get the case that this can be 4 cross 4. So in that case, m would be 20 and n would be 8. And then you can say it could be 2 into 8. In that case, m is 18 and n is 12. And finally, you could write it as 1 into 16. And in that case, m would be m minus 16. M minus 16 is 1. So m is 17 in this case and n is equal to 20 in this case. Right? Now, these are the possible solutions for this equation. But we also have to understand that the GCD and all should also be satisfied, right? So our possible answers are 32, 5, 24, 6, 20, 8, 18, 12, and also 17, 20. However, this is not the final answer because we have to check whether the GCD of m and n is equal to m minus 12 in all of these cases, and LCM is 4n minus 12. So if you look at the first case, what is the GCD of this? The HCF of this is 1, right? So actually this is not satisfying m minus 12. So we reject this case. The HCF here is 6 and 6 minus, this is also not satisfying m minus 12 because m minus 12 should be 12. So that is also rejected. The HCF here is 4 and 4 doesn't satisfy 20 minus 12. So this is also rejected. The HCF here is 6, but that satisfies 20 minus 12. And also the LCM is 36 and 36 is basically 48 minus 12. So this is a possible correct answer. It satisfies the conditions of the problem. This doesn't have the GCD is 1, so it doesn't satisfy. So basically you get 5 solutions out of this equation, but only one of them is the correct answer because only one of them satisfies the conditions of the problem, which were about the GCD and LCM of M and N. So the answer for this problem becomes just 18, 12 is your M and N. I hope you understand what I have done, the process by which we came to the answer. We first used the fact that product of numbers is equal to GCD times LCM. And after that, what did we do? We made it into an equation like this. And once we made it into an equation like that, we took 5 cases and then checked which of the answers are coming which satisfy the conditions of the problem. And we got only one pair, ordered pair. I hope it is clear. You can tell me if there is any doubt here, anything that is a problem in this one. Okay, it seems like it's fine. So we are going to move on to problem number 7. Okay. So problem 7, I had already stated yesterday. This question says, find all triples XYZ of real numbers such that 2x square plus 2y square, not 2y square, it was 3y square, 2x square plus 3y square plus 6z square is equal to 2 times x plus y plus z minus 1. So this is a problem where we have real numbers. So technically this is not a number theory problem. This is an equation. But there is a serious problem when you have an equation like this. The problem is that this equation has how many variables? It has 3 variables. And technically, if there is one equation with 3 variables, unless something special is happening, you cannot solve such an equation. Something special must be happening because otherwise you cannot solve for XYZ from a single equation, right? So this looks like an expression that is a quadratic in all the 3 variables. There are square terms for x square, y square, and z square. So what I will first do is bring everything to one side. 2x square plus 3y square plus 6z square minus 2x minus 2y minus 2z plus 1 equals 0. This is my condition now. And I have tried to bring everything on one side here. Okay. Now, what we need is to somehow think about how we can find the values of x, y, z here. One common technique in such problems, when there are multiple variables and there is a quadratic type of expression, what you should think of is basically, can we complete the square? Can we complete the square and express it as sum of squares? Express it as the sum of squares. Why is that going to be useful? So suppose I can express it as a sum of squares, x minus a whole square plus y minus b whole square plus z minus c whole square is equal to 0. Then obviously with a single equation, you can say that x must be a, y must be b, z must be c, right? Why does this follow? Because the sum of perfect squares can never be negative and it always has to be greater than 0. And the only way that the sum of the 3 perfect squares will be equal to 0 is if each of them is individually 0, right? So the idea here is, can we express it as some perfect squares, right? Now, if we are able to do that, we will immediately be able to find this value, right? Now, sometimes it is difficult to spot certain things like this. How to think of which things we need to make a perfect square and how to decide that. If you are confused, if you cannot figure out what numbers it will be perfect square of, you can just take a general case and hope that it works out. For example, I can do something like this. P times x minus a whole square plus q times y minus b whole square plus r times z minus c whole square is equal to 0. And here we are saying that P, Q, R, A, B, C belong to real. So what I am saying is that this expression, the above expression and the below expression are both equivalent, right? And what I want to find is the values of P, Q, R, A, B, C, right? So how do I do that? The way in which you can do that is try to find, like, try to expand this. And once you expand this, what you can do is match the coefficients. So let's try that on the next screen. So original quadratic is 2x square plus 3y square plus 6z square minus 2x minus 2y minus 2z plus 1 is equal to 0. What we will do is write it as p x minus a whole square plus q y minus b whole square plus r z minus c whole square is equal to 0. And expanding this, I get a px square minus 2apx plus pa square plus qy square minus 2qby plus qb square plus rz square minus 2crz plus rc square equals 0. So I have a px square plus qy square plus rz square situation here. And then I have a minus 2apx minus 2qby minus 2crz. And I have a plus pa square plus qb square plus rc square is equal to 0. Now, if I try to match this expression with the first expression here, what you should see immediately is that P is equal to 2, Q is equal to 3, and R is equal to 6, right? As soon as you realize this, then we start finding the other terms. So 2AP should be equal to 2. So P is 2, so A is equal to 1 by 2, right? And 2QB should be equal to 2. And therefore, B is equal to 1 by 3. And 2CR should also be equal to 2. So R is equal to 1 by C. So 1 by, or C is equal to 1 by R. So C is what? Basically 1 by 6. And now you can also confirm that this is coming out to be equal to plus 1. So what will happen here? 2 times 1 by 4 plus Q is 3. 3 times B square is 1 by 3 square plus 6 times 1 by 6 square. So you have 1 by 2 plus 1 by 3 plus 1 by 6. And clearly that is equal to 1. So basically the whole expression is matching and we have the values of P, Q, R and A, B, C. So once you have the idea that maybe I have to write it as a sum of perfect squares, we can easily find which are the perfect squares. So what is coming here is 2 times x minus half whole square plus 3 times y minus 1 by 3 whole square plus 6 times z minus 1 by 6 whole square is adding up to 0. And now since this equation is equal to 0, it's the sum of 3 perfect squares. So you get x is equal to half, y is equal to 1 by 3, and z is equal to 1 by 6. This is my answer for this particular question. And you have basically solved an equation that was having three variables and a single equation. And we are using the fact that sum of squares is always going to be greater than equal to 0. So that concludes problem number 7. The next problem states this: find the least positive integer n such that for any integer x power 4 plus n square is not a prime. This is the question. Now think about it. We have to find the smallest integer such that for any other integer x power 4 plus n square is not going to be a prime number. Right. Now, if you are familiar with this standard factorization, x power 4 plus, let's say, something square. Right. I will try to do the factorization of this when you take n is equal to 8, if n is equal to 8, right? If n is equal to 8, let's think of this number, x power 4 plus n square. What you will get is x power 4 plus 64, which you can write like this. X power 4 plus, you will add and subtract a middle term here in order to make a perfect square. So this is 8 square and this is x square. So the middle term will be 2 into 8 into x square. So it is 16x square is the middle term. So plus 64 and then you subtract the 16x square. And so this becomes x square plus 8 whole square minus 4x whole square. So that can be factorized now with x square plus 4x plus 8 multiplied by x square minus 4x plus 8, right? And even the inner terms here, you can understand this term by thinking of it as x plus 2 whole square plus 4. And the other term is x minus 2 whole square plus 4. So what we are getting is x power 4 plus 64 can be written as this expression, x plus 2 whole square plus 4 multiplied by x minus 2 whole square plus 4, right? Notice that each of these factors are greater than equal to 4 because you have a perfect square inside which is always going to be greater than equal to 0, right? So the number x power 4 plus 64 has been written in terms of two factors, right? And each of the factors is greater than equal to 4, right? So that means it has been written as a product of two other numbers, not just one and itself. So this number x power 4 plus 64 is definitely a composite number. Definitely composite because it has been written as the product of two different numbers other than 1 and n, right? So we have got the first situation where this number x power 4 plus 64 is not a prime, right? So this happens at n is equal to 8. We have to see whether it happens at a lower n or not, right? So let's think about it. What we want to show basically, or we want to check, is that if n is less than equal to 7, then x power 4 plus n square, whether it is a prime or not a prime. We already know that when n is equal to 8, x power 4 plus n square is not a prime, right? So we have to check this for any given integer x power 4 plus n square. So let's think about it. The question wanted us to say that find the least positive integer n such that for any integer x, the number should not be a prime. So if we can come up with examples, if we can come up with counter examples where by choosing appropriate x, we get that x power 4 plus n square is a prime for n less than or equal to 7, then those n have to be rejected. Those n will not satisfy the conditions of the problem, because if you can show that it becomes a prime number at even one x, then you cannot accept that n, right? Okay, so because for n is equal to 8, we have already proven that it is always going to be a composite number. So before that, if you can show some situations where it is a prime, then you will not accept the lower ends, right? So if n is equal to, n belongs to any of 1, 2, 4, and 6, then you can set x is equal to 1. Because what will you get in each of these cases? 1 power 4 plus 1 square, 1 power 4 plus 2 square, 1 power 4 plus 4 square, and 1 power 4 plus 6 square. And in all these cases, 2, this is 5, this is 17, and this is 37. These are all prime numbers. So for the cases n is 1, n is 2, n is 4, and n is 6, you can put x is equal to 1, and you are getting prime numbers for this, right? So those numbers are rejected. For n is equal to 3, you have x power 4 plus n square. You can put x as 10, and you will get 10 power 4 plus 9. So that will be basically 10,009. And you can check that this is prime. How do I discover that it is at x is equal to 10? You can check lower values of x. It is composite all the way through, but at this value x is equal to 10, it is prime. Similarly, if n is equal to 5, you can say x is equal to 2. X power 4 plus n square is becoming 16 plus 25, which is 41, which is a prime. So 5 is also rejected. So we have so far rejected 1, 2, 3, 4, 5, and 6. Now we have to take n is equal to 7. And in this case, the only value where you can take the lowest value of x is 20. You get 20 power 4 plus 7 square. And you can calculate this. This comes out to be 160049. And this is also a prime. Obviously, this will take a little bit of checking, but it comes out to be a prime. So what you can show is that for n less than equal to 7, x power 4 plus n square can be a prime for some choice, for some appropriate choice of x. Create choice of x. However, for n is equal to 8, we have shown that x power 4 plus n square is always composite, because we were able to factorize it in as a product of two numbers greater than 4, right? So therefore, our answer for this question is n is equal to 8. And that concludes this particular problem. Okay, let's move on to problem number 9. And in this question, we have to solve an equation. Solve in integers the equation x plus y minus 1 times xy minus 1 is equal to 2015. So we have to solve this particular equation in integers. So now, first of all, you have to think about it. What the key idea here is to first start thinking about the parity, right? The even odd nature, right? So on the RHS, you have odd, right? So both cannot be even, right? Even one of them cannot be odd, even. Even if one of them is even, what will you get? You will get an even number. So both have to be odd. Odd, and this also has to be odd. And now we need to understand what happens to x and y if both of them have to be odd, right? Let's think about it. Xy minus 1 is odd, so xy is even, right? And x plus y is also even. X plus y is even and xy is even, right? So xy is even can happen if x is even, y is odd, y is even, x is odd, or if x and y both are even, right? However, x plus y with even can happen only if x, either x or y, is even. No, actually this will happen only if both are even. Both are even or both are odd, right? If one of them is odd, one of them is even, the sum will be odd, right? So from this case and this case, the common solution, you have to see that the common thing that is there is both are even. That's how both the conditions will be true, right? So what we conclude is x and y are both even. And this conclusion came by analyzing the parity of both sides of the equation. So that is a common technique that you have to be aware of, right? Now think about it. If both are even, what can we say here? X and y are both even numbers. So if you think of the number xy minus 1, right? Xy minus 1 will be congruent to minus 1 mod 4. Why is that? Because x is some 2k and y is some 2m. So xy is going to be some 4km. So xy minus 1 will be 4km minus 1, which is clearly congruent to minus 1 mod 4. Right? Okay. Uh, right. And 2015, if we think about the factorization of 2015, we have that as 5 into 13 into 31. You can do that yourself and see. And we have here x plus y minus 1 times xy minus 1. Okay. And we have to think, we have to realize that xy minus 1 is congruent to minus 1 mod 4, or basically 3 mod 4, right? So what are the possible factors that xy can be? What are the possible numbers that xy minus 1 can be, right? Looking at the factorization of 2015, you should realize that the possibilities for xy minus 1 could be uh, you can get minus 65, minus 13, minus 5. You could get a minus 1. You cannot get a 1. you cannot get a 1 because 1 is not congruent to -1 mod 4, right? All of these numbers so far are congruent to -1 mod 4, right? And this whole thing has to be -1 mod 4. So here on the positive side, you could have basically 31. 31 is congruent to -1 mod 4. And you could have 31 into 5, which is 155, which is also congruent to -1 mod 4. If you do 31 times 13, you get 390, 403. So that is also congruent to -1 mod 4. And finally, you could have even 2015, which is congruent to -1 mod 4. So these are the possible values of xy minus 1, right? So from here, xy belongs to what set? Xy belongs to, you add 1 to all of these numbers, you get -64, -12, -4, 0, 32, 156, 404, and 2060. These are the possible values of xy, right? Now, what we also know is that x plus y whole square is greater than equal to 4xy. This is true for any two numbers, x and y, right? So if you think of the cases where xy minus 1 was -65, right? Then what is the other factor? The other factor is 31, -31, correct? Then only you will get this product. So then you can say in that case, x plus y minus 1 is -31. So x plus y is -30. And x plus y is -30. Then you have to check whether it is greater than equal to 4xy or not, x plus y whole square. So you also say 900 should be greater than equal to 4 times -64, which is true in this case, right? It is true in this case. So what I'm asking you to check here is, out of all of these possibilities of xy, there are so many possibilities of xy, right? You can, for each of these cases, you can calculate what is x plus y, right? Because if xy minus 1 is -65, x plus y is -30. Similarly, when xy minus 1 is -13, x plus y would be a certain value, right? And once you have gotten the corresponding x plus y values, you should check which of them satisfies this condition. Because this is an identity that is always true, because this is equivalent to x minus y whole square is greater than equal to 0, right? So since this identity is always true, out of the set of values, for some of them, it will not be valid, this identity, right? So you have to do this work. You have to identify out of the 8 solutions here, which ones are satisfying x plus y whole square greater than equal to 4xy. What we get is that we can restrict xy belongs to not 8, only these 4 possibilities, -64, -12, -4, actually 5 possibilities, 0 and 32. These are the 5 possibilities which satisfy the original conditions as well as the equation x plus y whole square is greater than equal to 4xy. And now for all of this, we can solve the system of equations. You get x plus y is equal to -30 and xy is equal to -64 here. You get x plus y is equal to -154 and xy is equal to -12 for the second case. For the third case, we have x plus y is equal to -402 and xy is equal to -4. For the fourth case, you have x plus y is equal to -2014 and xy is equal to 0. And for the fifth case, we have x plus y is 66 and xy is equal to 32. And solving these, we can get the set of solutions for our equation. And the set of solutions that comes out for us is -32, 2 for x and y, 2, -32, Then we have 0 comma minus 2014, and finally minus 2014 comma 0. These are the 4 solutions that you will end up with after doing this casework. So this problem is a little long, but you have to understand the key idea that helped us break down the problem. The key idea was the parity idea. Once you get the parity idea, you have to take cases and think about which cases are valid. And we used congruence modulo 4 to simplify the number of possible solutions. And once we realize that, we also check the fact that x plus y whole square must be greater than equal to 4xy for all of the possible solutions. So we don't have 8, but we have just 5 valid solutions. And after that, we solve it and see which ones are giving us integer values. So from these 5, notice that you got only 4 pairs of integers, right? So that completes this problem. Now let's look at problem number 10. This says, find the remainder when 3 to the power 2015 plus 7 to the power 2015 is divided by 50. Right. Okay. We have to find the remainder when 3 to the power 2015 and 7 to plus 7 to the power 2015 is divided by 50. Okay. Let's think about it. You can do it in many ways. One easy way to do it is by binomial theorem, where you can write it as 5 minus 2 to the power 2015 plus 5 plus 2 to the power 2015. Right? Once you do that, you will see that you will get the sum of these two series, right? This will only have certain terms. So for example, here I will write 2015 C0, 5 power 2015 and minus 2 power 0 plus 2015 C1, and this term will have a negative sign, 5 power 2014 and minus 2 power 1 and so on. And those negative terms will get cancelled. So what you will end up with is twice of 2015 C0, 5 power 2015 minus 2 power 0 plus 2015 C2, 5 power 2013 minus 2 power 2 plus 2015 C4, 5 power 2011 minus 2 power 4 and so on till 2015 C 2014, 5 power, this time it will be 1 and minus 2 power 2014, right? These are all the even terms, and this is in a bracket and it's multiplied by 2, right? So here you have to divide it by 50, right? So notice that 50 is what? 5 square into 2, right? So the second last term here, as a 2015 C 2013, no, not 13, 2012, and you have 5 power 3 and minus 2 power a large number, 2012. So this is equal to 0 mod 50, right? Because it has 5 higher power and 2 also higher power than 5 square 2, right? So this is 0 mod 50. All the terms here are 0 mod 50 till you come to, this is also 0 mod 50. Every term from here till the second last term is 0 mod 50. This is not 0 mod 50 yet, right? So what we have to worry about is the first term here and the last term here. So let's write them, but notice that you have a 2 outside also. So 2 times 5 power 2015 is the value of this term plus the last term. So 2 times, that is 2015 times 5 power 1, and there is minus 2 power 2014, right? And now notice that this is basically going to give us a, this has many powers of 5 and it has 1 2, so this is also 0 mod 50, right? And this has a 2 here, and a 5 can come from here, and this is a 5. So again, this is also 0 mod 50. So overall, the whole expression is 0 mod 50, and that is one solution. So our answer is remainder is 0. And this solution was by binomial theorem. There is another second solution that I will tell you. The second solution is this. So let's think about, we have to find the remainder when 3 power 2015 plus 7 power 2015 is divided by 50. Okay. Now notice first of all that 3 power 2015 is odd and 7 power 2015 is odd. So it is obvious that 2 divides 3 power 2015 plus 7 power 2015. So that is a true statement because it's the sum of two odd numbers. So 2 clearly divides it, right? Okay. So now we have to worry about whether does 25 divide 3 power 2015 plus 7 power 2015. This is the question right now, correct? So by Euler's theorem in number theory, we know that 3 power 20 is congruent to 1 mod 25. And also 7 power 20 is congruent to 1 mod 25. These are two things that I want you to get back to Euler's theorem and prove that by Euler's theorem you can conclude this, right? So check out Euler's theorem and see whether this is correct or not, right? Using this fact, we can say that 3 power 2015 plus 7 power 2015 will be congruent to 3 power minus 5, because this is 2020 minus 5 and 2020 would be 1 mod 25, right? So this is congruent to 3 power minus 5 plus 7 power minus 5 when you do mod 25. And that will be congruent to, so this is 3 power minus 1 to the power 5 plus 7 power minus 1 to the power 5 mod 25. And mod 25, you have to find the inverse modulo 25. So you should realize that the inverse of 3 modulo 25 is basically minus 8. 3 into minus 8 will give minus 24, which is 1 modulo 25, right? So what you will get here is minus 8 power 5, and inverse of 7 would be minus 7, because again you're getting minus 49, right? So plus minus 7 power 5. I'm writing the inverse of these numbers modulo 25. Again, this is a concept in number theory that you need to be aware of. How to take inverse of a number modulo a particular number. So this is what is coming. And from here, we can write it as minus 8 power 5 is congruent to minus 2 power 15 basically. And right. So this is minus 2 power 15 minus 7 power 4 is modulo 1. 7 power 4 is 2401. So that is modulo 1 mod 25. So 7 power 5 would be simply minus 7. And what we are getting is minus 2 power 15 minus 7 mod 25, which is congruent to 2 power 5 minus 7. This part is following because you have to do modulo 25. So like you have to check this fact. This should become 32 minus 725 mod 25, which is 0. So 2 power minus 2 power 15 is, I think it's simple calculation. 2 power 10 is 1024 and 1024. Oh yeah. 2 power 10 is 1024, right? And 1024 is minus 1 mod 25. So 2 power 15 is 2 power 10 into 2 power 5. So therefore, this is all minus 1 and minus 1. So minus 2 power 5 you're getting. And therefore, the minus sign goes away. So this becomes 0 mod 25 again. It follows because I know 2 power 10 is 1024 and this is minus 1 mod 25. So therefore, this can be simplified like this. So that is another way, but this one uses Euler's theorem. You could also do it by Fermat's theorem if you use the fact that you need to know this fact that if P is an odd prime, P is an odd prime and P divides m power P plus n power P, then P square also divides m power P plus n power P. We have to use this fact here. So try to think on these lines also. So you basically will be able to say that if P square divides m power P plus n power P, so if we know that 5 divides 3 power 5 plus 7 power 5, you can calculate this and check. Pi divides this. And therefore, it will imply that 5 square divides 3 power 5 plus 7 power 5. And then you will have 2 into 25 divides 3 power 5 plus 7 power 5, which divides 3 power 2015 plus 7 power 2015. So ultimately you get 50 divides this and this thing divides this. So it can be done, but again, you will have to prove this statement. This is also something that you can try as an exercise. Try to use Fermat's theorem to try to prove this statement. The first solution that I said, the binomial theorem solution, is the easiest one. So you can look at that and that will probably help you explain this particular problem. So that's it for today's class. Tomorrow again, we'll come back with more problems and let's discuss more questions relevant to your IOQM and RMO. Every day we are doing problems. Please join the live class if you can. The link to the live class has been shared in my channel. So it is on a post. It's on a post on my channel, community post. And if you want, you can ask for the link in the comments below the video, and I will send you the link. join the live class. You will benefit from it. We'll continue the classes till IOQM. So hopefully we will cover so many problems and you will benefit a lot from. So see you in the next class. That's it for now.